Hello and welcome to the video lecture series brought to you by St. Andrews Institute of Technology and Management. And we are discussing the subject called Data Structures 2. And today we are going to start with a new topic called Introduction to the Binary Search Trees, that is BST. I think you people are more than familiar with what are the binary trees. Okay, as you people have already gone through yours the course in your previous semester, that is your data structures, the beginners level. And in this particular subject called data structures advanced level or 2, we are going to focus on a very special kind of binary search tree. The binary search tree is a tree which is allowed to be have only two children. That is, a single node can have only two children at a time. Okay, that is left and right. Although this is a very layman term that I have told you, but it will give you, let's say, an idea what I am trying to say. Okay. Now, if we start with binary search tree, let me first give you the formal, let's say, the formal definition of your binary tree. So, a binary tree T is defined as finite set of elements, and those elements are called nodes. Okay, such that if T is empty, then there will be no nodes inside your binary tree. Secondly, T contains a distinguished node, let's say R, and we normally call that particular node as root node, that is the first node of your tree. And the remaining nodes of T form an order pair of disjoint binary trees, that is T1, T2, and then so on. Okay. Now, if T does contain a root R, that is, it means that is the tree is not empty actually. Then the two trees, that is T1 and T2, are called as left and right subtrees of the root. Okay. Let's get back to the nodes. What I am trying to say, it will be more sense. So now this is your example of a binary tree. So what I am talking here is, if this tree is empty, then there will be no nodes, and each of these data points are called as nodes. And let's say if it has a node that is called R or root, it will be the first node every time we are going to look for anything in a binary tree. Okay. Now it will have two childrens, that is a left and a right subtrees. Those left and right subtrees could be, let's say, a single nodes, or could be multiple nodes. But in the end, left and right subtree then again will be a binary tree in action. Okay. Normally, those left and right are called left successor of the root or right successor of the root. Or if the node is not your root, then in that case, the left and right subtrees will be called as the left successor of the node and right successor of the node. Okay. So I think I think you must have recalled until now that what is a binary tree. Let's move ahead to the binary search trees. So binary search tree is a very special kind of binary tree. Okay, now according to the notes I have provided to you, it is called a binary tree because each node has maximum of two children. Okay, so binary tree has the property that the maximum number of children a node can have will be 2. And it is called a search tree because it can be used to search for the presence of a number in your big O notation log n time. So the time to search for a particular number in your binary search tree is quite less. Now the properties of that separates a binary search tree from a regular tree is, all the nodes of the left subtree are actually less than its root node. So what I am trying to say here is, suppose this is your binary search tree. Let me again tell you that all the binary search trees are binary trees at first. Okay, so you can see that every node has only two children, that is left successor and right successor, or you can say left subtree or right subtree. in a binary subtree, in a binary search tree, all the left nodes or all the nodes in a left subtree are actually less than the root node. So you can say that now 8 is your root node, as we have already discussed. The first node that we are going to encounter in a search tree is your root node. The first, because you can call root node as a node which has the property that it has no parent. Okay, it has no parent of its own. So this particular node has no parent of its node. You can call that the parent of root first or root node is null. Now, as you can see, the left hand side successor or the left subtree of this particular node 8 has all the values which is actually less than the root node. Okay, so let's look if it is right or not. The root node has a value of 8. Okay, the root node has a value of 8. The values in the left subtree of this root node is 3, 1, 6, 4, 7. And each one of those values in these nodes of the left subtree is actually less than your root node, which has a value of 8. And similarly, all the nodes of the right subtree are actually more than the root node. By saying more than the root node means the value in the right subtree of a root node are actually more than the actual value of the root node itself. So the root node has a value of 8. The right subtree has 2 nodes. The values of these 2 nodes are 10 and 14. So as you can see, in this particular example, the root node has a value of 8 and all the values to the left of it, that is the left subtree, has a value less than root node value, and all the values to the right hand side of the root node has a value less than root node. So this makes your binary search tree, or BST sometimes you call it. Now I have also mentioned here an example that what could not be a binary search tree. So as you can see here, all the values to the left hand side of the binary search tree of the root node in the binary search tree of this root node 8 is actually less than the root node value. So first criterion is okay. Second criterion is all the values in the right hand side subtree of this BST is less than its root node. Yes, that is also right. 10 and 14 is actually greater than 8. So it is also right. Now let me come down. I have already told you that the left hand subtree and right hand subtree in a binary search tree is also a binary search tree in itself. It means this left hand subtree should be a binary search tree in itself, and this right hand subtree must be a binary search tree in itself. That means if this is your node and you look to the children's in the right and left hand side, they must towards the left hand side the value must be less than its parent, and towards the right hand side the value must be less than its parent. Greater than its parent. So as you can see here, the value of this parent is 3, and to the left hand subtree the value is 1, and towards the right hand we have the values 6, 2 and 7. Now as you can see, towards the right hand side all the values of the nodes in the right hand subtree must be greater than the parent node. That is, all these values must be greater than 3 in this case. But 2 is a violation here, because 2 resides in the left hand side, 2 resides in the right hand side of the subtree of a binary search tree, but the value, one of its nodes value is 2, which is actually less than 3. So it must end up in the left hand side tree. Okay, so I think you have got the point now. So this is not a binary search tree. Although it is a binary tree, but it is not a binary search tree. So you have to check at every node until the leaf nodes are reached. So every node which is not a leaf node must qualify the rules of binary search tree. That is, all the values to its left hand child must be less than itself, and all the values to the right hand side of itself must be greater than its parent. Okay, so this is your basic definition of your binary search tree. Let me iterate the formal definition of your binary search tree. A tree T, let's say the name is T, it is called your binary search tree if each node n of T, n is the name of the node and T is name of the tree, is has the following properties. First is the value at n is greater than every value in the left subtree of n, and is less than every value in the right subtree of n. Okay, so I think this is actually what we have seen in this particular example, that if this particular tree is let's say named as T and this node has named as n, then every value which is to the left hand side of this node n must be less than the value n, and every value which resides on the right hand subtree of this node n must be greater than this value. So every value in this particular left hand subtree must be less than 8, and every value towards the right hand side of this node, that is 8, or the right hand subtree, must be greater than 8. Or you can say all of these values towards the left hand side must be less than all the values in the right hand side. Okay, so as you can see, 3, 1, 6, 4, 7, all of these values are actually less than 10, 14. So these are the two ways you can define your binary search tree, either by the left hand rule or right hand rule, or by stating that the left hand side must have the values less than node and all the values on the right hand side must be greater than the values on the left hand side of the tree. Okay, so this is your basic definition of binary search tree. I have already told you what would be the time complexity of finding out or searching out a particular element or a particular node is the time complexity, has the time complexity of log of n, where n is the total number of nodes available in a particular tree. So I think you people have got the point what I am trying to say. Let me traverse through these nodes quickly. So the algorithm, now the first algorithm is if a particular value resides inside a binary search tree or not. So we are done with the basic definition of your binary search tree. Now the first algorithm is how you are going to find out if a particular value is in your binary search tree or not. Suppose we want to find out if the value 7 is inside your binary search tree or not in this particular example. So what we are going to do is we are going to start with the root node. Okay, now from the root node we'll compare the value we want to search. Now we want to search the value 7 and root node has a value of 8. So we are going to compare them. Now 7 has a value less than 8, and according to binary search tree rule, all the values less than the root node must be on the left hand side subtree of the root node. So this is your left hand side subtree. So it is now clear that your value is not in your right hand side subtree. Okay, so suddenly your search area is reduced to half, nominally. Theoretically, at least, if it is a complete tree, then theoretically half of the tree you have discarded already. So that is why searching out a particular element in a binary search tree is so quick. Now we are going to compare the value to be searched with the next node. Now next node has a value of 3. As you know, the value of 7 is greater than the value of 3. So according to the binary search tree rule, again all the values which are greater than the parent node must be on the right hand side subtree of the parent node. So this parent node 3 has a value of 3. Its right hand subtree, that is this particular tree, must have all the values which are greater than the value of the node. Now 7 is greater than 3, so we'll go for looking towards the right hand side. So now we have discarded the left hand side portion of this. Again we have shortened our search area to a great length. Now we'll compare the value with the next node. Now the next node has a value of 6, which is actually less than the value to be searched, which is 7. So if the value exists in this BST, it must be towards the right hand side of the node 6. So we'll go to the right hand side, and now again we will do the comparison. At this comparison we'll find out the value we are searching actually is 7, and this particular node has a value of 7. So your value has been searched now. If this particular node has a value, let's say not 7, at least let's say I don't know, we have to take a different example, but let's say if it is not 7, then in that case we will stop the searching because we have already reached the leaf node. And as you know, the leaf node has no childrens. So we'll stop our searching and return null. That is, the element has not been found in your binary search tree. So we're going to see that particular searching algorithm in great detail in next lecture. The searching and insertion, we'll see both of these algorithm in the next lecture. In this lecture, I have just given you the idea how to particularly search for an item, how your algorithm is going to be defined if you try to search a particular item in your binary search tree. So for in comparison to your normal binary tree, searching in binary search tree is much faster. Okay, so I'm going to end this lecture now. Thank you.